Over 2,000 years ago, in a bathtub found in the Greek state of Syracuse, a fundamental principle in experimental physics was unraveled. While taking his regular evening shower in the bathtub, Archimedes realized that the water was rising the more and more he submerged himself. It was at that moment that he knew. An object fully or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid it displaces. And so the story goes. Archimedes made the most dramatic bath exit in history, naked and screaming, "Eureka!" Which translates to, "I figured it out," or, "I need a towel."
Although the story may just be a legend, Archimedes' principle is not. An object in a fluid will be subject to an upward force exerted by the fluid, which is equal to the weight of the fluid displaced by the object. Now this principle can be expressed by the formula buoyant force is equal to density times volume displaced times gravity, where the units of buoyant force is in newtons, the unit of density is in kilograms per meters cubed, and the unit of the volume displaced is in meters cubed. And G is of course the gravitational pull of the Earth, 9.81 meters per second squared. Now, Archimedes' principle can actually be related to Newton's second law of motion, force equals to mass times acceleration. And this is because when an object is submerged in a liquid, it experiences the downward pull of gravity and the upward push of the buoyant force. Now, the net force can be calculated by subtracting the buoyant force from the force of gravity. When an object is in static equilibrium, meaning F net is zero, then the buoyant force will be equal to the force of gravity. 3 different scenarios can be explored for static equilibrium. In the first scenario, the buoyant force is equal to the force of gravity, and the density of the object is lesser than the density of the liquid. In this scenario, the object floats above the liquid. In the second scenario, the buoyant force is still equal to the force of gravity, but the density of the object is greater than the density of the liquid. In this scenario, the object floats under or just inside the liquid. In the third scenario, the buoyant force is less than the force of gravity, and the density of the object is greater than the density of the liquid. In this scenario, the object sinks. We explored 2 of these scenarios in our lab. Now, why did we do this lab? The objective of the lab is to determine how Archimedes' principles, specifically buoyant force, is affected by the mass of the object, the volume of the fluid displaced, and the density of the volume. Another goal of this lab is, of course, to create and execute methods and procedures that can be used to analyze the dependence of buoyant force of mass, fluid density, and volume displaced. Now, I think
that's enough. So boring. Okay. The purpose of activity 1 is to set the apparatus needed to calculate the buoyant force using the force sensor and Pasco 850 interface to the force motion sensor, and then calibrated it, setting the standard to 0 newtons and the force value to 4.90 newtons. Then we measured the masses of the cubes and converted that to kilograms. We mounted the cubes on a string and measured the force acting on them in the air using the force sensor. We then found the force acting on them in water using the same force sensor and calculated the buoyant force by subtracting force of air minus force of water. For our next experiment, we sampled 5 different weights of masses 20, 50, 100, 200, and 300 grams each of the same density. We collected 210 milliliters of water in a 250 milliliter graduated cylinder. We then put the weights in water one at a time and read the final volume on the graduated cylinder. Again, we calculated the buoyant force by subtracting the force from the air minus the force from the water. For our final experiment, we added salt and water to a large beaker and heated it to dissolve it. We then measured a mass of 100 grams over several trials of adding more salt to the beaker. Again, we used the force sensor to find the force and calculated the buoyant force. We actually tried this experiment with orange juice and milk. However, this did not work because the density difference between these liquids and water was too minor.
Nobody cares about that. We only care about what our results are. So let's talk about our results. Okay, for this instance, we investigated the dependence of the buoyant force on the mass of the object. So we had 7 different trials with 7 different items, aka aluminum, steel, brass, copper, acrylic, PVC, and nylon. We measured the mass in grams and converted that to kilograms. We then measured the force in water using the force sensor and the force in air also using the force sensor. And then to calculate the buoyant force, we said force air minus force water. We then graphed this in a buoyant force versus mass graph, and our trend line was a linear trend line with the equation of y equals 0.0248x plus 0.1268, and our r squared value was 0.0476. our measured true value was 0. So we are somewhat fairly close to the true value of 0, as there is not supposed to be a correlation between mass and buoyant force. Additionally, our absolute error was 0.0248. Our R-squared value of 0.0476 is not very close to 1, meaning our data points were not very close to each other. Because the true value was 0, we cannot calculate percent error because we cannot divide by 0. Therefore, we calculated percent difference, and our percent difference for this experiment was 2%.
For our third experiment, we investigated the dependence of buoyant force on the volume of the fluid displaced by the object. We did 5 trials with objects of mass 20 grams, 50 grams, 100 grams, 200 grams, and 300 grams. Our initial levels and final levels in milliliters are shown in the table, along with our volume. We calculated the final buoyant force by subtracting the force of the water minus the force of the air. Our expected value was 9,800, and our percent error was 0.99%. which can be shown in our buoyant force versus volume graph. Our R-squared value was 0.9992, and our equation of the line was 9,897.1 for our slope, and our y-intercept was negative 0.0002.
For our third activity, we were to investigate the dependence of buoyant force on the fluid density. For this, we did 5 trials with various increments of added salt. So for the first time, we added 5 grams of salt and then added progressive amounts of 3 grams of salt until we got to the total amount of 14 grams of salt. We used a weight of 50 grams, measured that in its actual weight, calculated the volume of the water, and then we also, after heating up the salt and adding it to the water, calculated the force in water and the force in air. To get to the buoyant force, we said force of air minus force of water, and we calculated our total volume in meters cubed.
We then graphed this in a buoyant force versus density graph. Our trendline equation was y equals 0.0038x minus 3.768, and our R-squared value was 0.934. As our R-squared value is relatively close to 1, this means our data points were not only close to each other, but were also more or less precise in their measurement. Our true value is 0.004925. This was calculated by taking the volume of the fluid displaced times gravity. Comparing this to our slope of 0.0038, we get the percent error of around 22%. Our units for our slope are meters to the power 4 divided by seconds squared.
In conclusion, our first 2 experiments were successful, while the results for our last experiment were a little bit further off. For our first experiment, the absolute error was 0.00248 newtons with a percent difference of 2%, which indicates high precision and accuracy. Our R-squared value was 0.0476, which is a low R-squared value indicating no defined relationship between our data values, which is good because there is no correlation between mass and buoyant force. Our second experiment yielded a slope of 9,897.1 newtons per meters cubed with a percent error of 0.99% and an absolute error of 97 newtons. Our R-squared value was 0.9992, indicating a very strong correlation between volume displaced and buoyant force. Tiny discrepancies can be attributed to systematic errors in the experiments such as loss of water, calibration of the force sensor, parallax error when taking measurements, and repulsive forces between the strings molecules and the water molecules. Random errors might have contributed to the discrepancies. For example, unknowingly shaking the table. Our last experiment was not quite as successful as the other 2. After trying the 2 different liquids, which included a high-protein milkshake and orange juice, to change the density of the water, we finally decided to use salt and water, which gave us a slope of 0.00 quartic meters per second squared, which differed from the expected value of 0.0005883 quartic meters per second squared. Our percent error was a 21%. A large cause of this might have been that initially we weren't taking into account the volume of water displaced. Another probable cause is an overestimation of the salt measurement. Although that one wasn't quite ideal, this particular experiment taught us that real-world measurements don't always go as expected. One question that came to mind was, are submarines able to control their own density and their buoyancy such that they can operate at and stay at different depths, either by they could float on the surface or get into it? Submarines typically carry tanks on them that they can fill with either air or water, depending on the density that the submarine needs in order to float at its required depth of operation. So for example, at the surface, those tanks can be filled with air in order to lower the density of the submarine such that with the lower density air in the tanks, the submarines will be able to float on the surface, whereas if the submarine needs to descend and needs more density to do so, the tanks can expel the air and can then be filled with water from outside in order to accomplish that. And then the submarines will also carry on them compressed air in order to do so.
Archimedes wasn't just taking a bath, he was discovering why your rubber ducky stays afloat. Remember, it's all about that buoyant force pushing back against gravity. So next time you're in the tub, think of yourself as a physics genius in the making.